Today is our first main day on statistics. Here in our probability and statistics class, we've talked a little bit about statistics, but now we're really getting into it. It's not the kind of statistics that you get in a basic statistics course that focuses a lot on data, though that is in the background, and we will talk about data. It's more of a mathematical statistics. We want to understand mathematical statistics from a theoretical perspective because it's useful for you to know. Mathematical statistics is not this abstract pie in the sky kind of thing that's not useful. It is very useful. It is the basis for practical applied statistics. You need to know mathematical statistics. It is, I think, just like probability, a prime example of mathematical modeling. We are doing modeling in a real satisfying way, I think is the best way to describe it when you really get into it. And the key initial concept is that you have a population. Pretend this box represents a population. Now, when I use these words, they mean slightly different things depending on how you want to think about them. When people who do basic statistics think about the word population, and when I say basic, I don't mean just people who are taking intro statistics. I mean people who use statistics on the job as well in some good, important ways. Most people think, okay, population, that must be like a bunch of people, like the population of the United States, or maybe a bunch of companies. All the companies in the United States that have revenue above $1 million a year or something, or a population of cars that are manufactured in the country in a year or something like that. And that is a fine way to think about the word population, and we can even initially imagine it that way here right now. But mostly in our class, in our mathematical statistics that we do, we are going to think about populations as related to random variables. But hang on. When we've got a population that we'd like to study, for us, it'll be a random variable that we like to study. How do you study it? You need some data, effectively, is the way most people think about it. Data that comes from a sample. You can't observe, for example, the average height of everybody in the country because it's just not practical to go around and measure every single person's height and that kind of thing. That's not practical. So you need a sample from that population. And ideally, you want it to be a random sample. Why? Because if it's a random sample, then the intuitive idea is that you hope it reflects the population, at least if the sample size is large enough. Now, sample of size 1 is not necessarily reflective because if you're talking about heights of people, you might pick a basketball player. All right? You want samples that are relatively large in size. How large is large? Well, it depends. Maybe 50 is large enough. Maybe a couple hundred is large enough. Maybe it needs to be a couple thousand. Random sample of size a couple thousand to be reflective of the population in a way that gives you good information about the population. And yes, you want it to be random. That's the best way to get a sample that's reflective and unbiased. You're not purposely picking basketball players to estimate the average height of everybody in the country here. Okay? Populations, when you think about them this way, are described by parameters. Described by parameters. And random samples are described by statistics. And it's one of the very fortunate times in this class that occurs more than once where, oh, this is great. Population and parameter both start with P. Sample and statistic both start with S. How fortunate. P goes with P, S goes with S. Parameters are numbers describing the population, like the average height of everybody in the country. And if everybody, including babies, is too broad a category, okay, maybe you say everybody who's at least 20 years old. Talking about full-grown adults, okay? Sorry if you're 18. Okay, 18 and over, whatever. Okay? That would be some fixed number, but think about it. What is the average height of everybody in the country? Nobody knows, except God. Nobody knows what it is. But maybe we can estimate it? Yeah, probably. By getting a good random sample, making good measurements, and computing an arithmetic average. That would be computing a statistic. Add up all the heights and divide by how many people you measured. That would be an arithmetic average that should hopefully estimate the true population mean for everybody in the entire country. Okay, that's how most people think about this. All right, we're doing mathematical statistics, so we need to be a little bit more abstract for good reason, because we want to apply probability. That's the good reason. So for us, a population really is more of an unknown random variable, you might say. A random variable X. Population is going to correspond to a random variable X. That might be discrete, it might be continuous, might be mixed with, well, in most practical situations, you don't really know for sure what the distribution of X is with some distribution. I mean, usually you're able to identify if it's discrete or continuous based on the situation. Are you counting, doing a count? Or are you measuring a length or an amount of time or an area? The first case, a count would be discrete. Measuring a length of time or an area would be continuous. But as far as what its PMF would be in the discrete case, or its PDF would be in the continuous case, what those functions would be, probably nobody knows, except God. Nobody knows, but maybe we try to make a guess, make an assumption, make a model, assume it's got a normal distribution is the most common model, or maybe an exponential distribution, or maybe a chi-squared distribution, gamma in general. Or in the discrete case, might be binomial often comes up in real clear situations like shooting free throws and that kind of thing. Poisson. We make assumptions. We use maybe well-known random variables that we've studied in chapters 3 and 4 as models for the distribution of X. Assume that they're good models and then see what you can figure out from that. The statistics for us here and the random sample, in fact, are also abstract. The random sample consists of a list of random variables. Those are supposed to be capital X's there, just like this, the capital X. I think again, Dr. Wetzel makes the Roman numeral X's to emphasize their capital X's. I just don't bother. These are capital X's. It's a list of random variables and random variables that are assumed to come from the same distribution as X, and they're also assumed to be independent. That's a random sample for us. This is a list of n independent random variables with the same distribution as X. That's an assumption. It's an assumption for the sake of doing some theory. The theory has applications. Independence. The observed value of x1 doesn't help us predict the observed value of x2 or the observed value of x3 intuitively. What does this technically mean? Technically, it means the n-dimensional joint distribution, which we've never talked about before. We've always kept ourselves to bivariate random variables. But you can generalize bivariate random variables, chapter 5, to trivariate with 3 variables, or quadvariate with 4, or n-variate with n of them. The joint PDF in the continuous case, or joint PMF in the discrete case, is the product of the marginal PDFs or PMFs. That's what technically independence means. These are the joint, that's the joint, and these are the marginals. Or if you knew what the marginals were ahead of time, you define the joint to be this product. And if these have the same distribution, in fact, all these marginals are the exact same functions, though you would plug the different variables into them, x1, then x2, then x3, and et cetera, to get a product that would be your definition of the joint. Technically speaking, that's what the assumption of independence would imply. Does that mean we're going to have to do n-dimensional integrals? We can mostly avoid them. Completely? Well, yeah, in this class we can completely avoid them. But if we were going to do some real advanced theory, we'd have to think about triple integrals, quadruple integrals, quintuple integrals, n-dimensional integrals. Though this assumption would make things easier than they would be otherwise. So effectively, again, this means you're defining the joint PDF or PMF to be the product of these marginals. And again, the formulas for each of these Fs would really be the same because they all have the same distribution, though you do plug in the different variables into them, so you get a formula that involves all n variables. That's what it means. We don't typically have to worry about that, though, in our class. What's a statistic? A statistic is a function of the random sample. Statistic is a function of the random sample. The most common function being the sample mean. Sample mean, symbol is X bar, capital X bar. It is a function of the random sample. I'm going to use a different letter than F, though I'll call it H. That's, you know, if you think back to chapters 3 and 4, that's a common letter used for functions of random variables. Some function of this random sample. These are all capital letters here. What function? Well, add those random variables up and divide by how many there are. It's an arithmetic mean. But realize this is a theoretical kind of object. It's a random variable because it's a formula involving a bunch of random variables. It's not a bunch of numbers. Capital X bar is not a number. It's a random variable. We can observe a value of capital X bar based on a random experiment and getting observed values of the capital X1 through capital Xn and actually adding numbers up and dividing by n. That would be an observed value of capital X bar. Call it little x bar. That's what most people are used to doing since, what grade did they teach you about means? 5th, 6th, 7th grade, something like that. You learn a little bit about averages. And on the job, people are computing observed values of the sample mean. But this thing is an abstract. idea. I hinted at this a week ago, right? We were talking about adding independent random variables, x plus y, and then we also averaged them x plus y over 2, and we did some double integrals over triangles to help us figure out distributions. And for example, with the uniform distribution, if x and y had a uniform distribution on 0, 1, when x plus y had a uniform distribution on 0, 2, and its PDF had a graph that was a triangle instead of a horizontal line. Remember that? And with an exponential, we added 2 exponential functions that had a mean of 1. And we got a gamma distribution with a alpha equal to 2. A week ago. 7 days ago, or was it 9 days ago? It's last week sometime, okay? That was what we were doing. We were doing this with n equal to 2. And I was also hinting at something called the central limit theorem. This is important to think about this stuff theoretically. It's important if you're really going to get what's going on in these next few weeks. We do apply it to situations where we have data, but it's important that you understand the theory. So let's start trying to apply this. And let's start by trying to apply it to one of the exam problems, this one, where we've got a PDF that we are defining to be a constant times x squared over the interval from 0 to 2. So effectively, we're thinking of this as like our very own little distribution that we feel like thinking about. PDF. The c ended up being 3/8. So it's 3/8 x squared if x is between 0 and 2 and 0 otherwise. The graph of the PDF. Oh, let's see. When you plug in 1, you get 3/8. When you plug in 2, 2 squared is 4. You get 1.5, I guess. So if this is 1 here and this is 2 here, the graph looks about like that. It's quadratic. It's 0 otherwise. I made these less than or equal to, so technically we'd have open circle down there. But again, with a continuous random variable, it wouldn't matter if I use less thans. So there's our PDF. What's our application? I'm not saying. Try to imagine a situation where you've got data that you're trying to model in such a way that this is a good model, meaning all the data values are between 0 and 2, first of all. Nothing bigger than 2, nothing less than 0. Second of all, they tend to cluster closer to 2 than they do to 0. The density is higher near 2 than it is near 0, pretty significantly higher. A little bit more technically, the area under this graph over any region, for example, from 1 to 1.5, is the probability of observing a value between 1 and 1.5. And if you got a lot of data, say 1,000 data points, that should be very close to the percentage of the data between 1 and 1.5. But not just for that interval, but for any interval between 0 and 2. You might think that's an impossible task. How can you get that to match exactly? You probably can't. It's just a model. You just hope you don't hope it's perfect. You hope it's pretty good. But that's what happens in modeling, is you just hope things are pretty good. Not perfect, pretty good. That works really well in physics. Your models can be really good. Less well in, say, psychology. Your models are just like pretty good, or maybe just okay. You know, physics is a hard science with real exact equations. You might say, are they perfect? No, you got to make some assumptions still there. And, you know, general physics is different than modern physics. Newtonian physics is different than Einsteinian physics and quantum mechanics. Don't worry about details. They do make slightly different predictions in certain situations. Use Newtonian physics to build bridges and buildings. Use modern physics to send spaceships off to Mars or whatever, or do GPS. Actually, you have to take relativity into account with GPS systems. It depends on the application, which one you want to use. So modeling is never perfect. You just hope it's pretty decent. Good enough to, like, make business decisions about, or life decisions, and not lose money or not, have bad things happen to you. So that's our PDF. What's the mean? The mean is the expected value of the random variable, which is in this case going to be the integral of x times 3/8 x squared. And I think pretty much everybody got this right. The mean does turn out to be 1.5. The density is so much higher near 2 that on average, data is a lot closer to 2 than it is to 0. You should expect a mean closer to 2 than to 0. The mean is the center of mass. If you imagine the region under this graph as being like made of a thin sheet of metal, and imagine the x-axis as being like a seesaw, the mean is where to put the balance point. Is that a useful thing? Probably not, but it's nice to imagine geometrically to try to kind of eyeball where the mean is. So what is that? That's a parameter, mu, a population mean, really. If this is my population distribution, this is the population mean. I know what the answer is here because I'm assuming I know what the exact distribution is. What happens with the random sample? What about capital X bar and its observed values? Will they be close to 1.5? I mean, the formula for capital X bar is different. It's an arithmetic average. Add these things up and divide by n. This means an integral. Those are technically different things. Should we expect X bar to be close to mu? I use the word expect purposely as like a pun. Is the expected value of X bar the same as mu? Amazingly, yes. X bar turns out to be what's called an unbiased estimator for mu. This is very important. Capital X bar is an unbiased estimator for mu. Each word there is important in each symbol. Capital X bar, our statistic, sample mean, is, yes, that's important, and yes, that's important, as opposed to the, because there could be other unbiased estimators as well. An unbiased estimator for mu. An estimator is a statistic. X bar is a statistic. It's a function of the random sample. There could be other statistics that could be estimators for mu besides X bar. Like what? Maybe the sample median? Means and medians are different though, so maybe not. Maybe something else? Maybe for some silly reason we subtract 1 over n squared from this or something. That would be weird, but doable, I guess. Could that be an estimator for mu as well? It could be. And maybe even it would be a good estimator when n is large, because 1 over n squared would be close to 0 when n is large. So it's not, with the large sample size, it should be a good estimator. It's weird, but should be good when n is large. This is a lot more simple and logical. It's a logical estimator. What does it mean to say it's unbiased? This means, oh boy, I'm so glad I used the word means there. It means It means the mean of the mean is the mean. And I mean it. I'm so happy I got to say that. It means the mean, expected value of the mean, sample mean, is the mean, population mean. Mean of the random variable x. Yeah, that's the same as this. Why? What? Remember, x bar is a statistic, and therefore it's a random variable because it's a function of random variables. It's got a distribution. It's got an expected value. How would you find this expected value? Do an n-dimensional integral of something times this, maybe? No, we don't have to do that because this is true. We can just say it's the same as the population mean. But why? You don't have to do n-dimensional integrals to verify this. You can use properties of the expected value operator. Not right now, but soon we will use properties of the expected value operator to verify this. And yes, this means the mean of the mean is the mean. This means, as an ordinary use of the word mean, expected value is a mean, right? Sample mean x bar is a mean. Mu is a mean. This means the mean of the mean is the mean, and I mean it. You having fun today? Okay, what does that mean? Let's use Mathematica now to do some simulation with our user-defined PDF. You know, this is not a parametric PDF. It's not a gamma. It's not a exponential. It's not a chi-square. It's not a normal. It's user-defined. We're defining it. Can Mathematica handle that? Yes, it can. Of course, because Mathematica can do anything. I typically need to look in the help menu for this, the documentation center, to remind myself how to do it. The key command besides RandomVariate, which we've used before, is probability distribution. Okay, and as always, it's probably most useful at first to just look at the examples, maybe copy and paste an example. What's going on here? So probability of distribution, this evidently is a PDF over the entire real number line. And this kind of code, what is it doing? It's not clear what it's doing, but let's copy and paste it anyway. And modify it in a way that makes sense here. How about change the f of x to 3x squared over 8? And change the interval probably from 0 to 2. And what's this d here? Well, that's just the symbol that this is storing something in. I just entered it. That's okay. Semicolon just suppresses output. If I get rid of the semicolon, I think we don't see much. It just says same thing I typed in essentially. It's got a distribution. It's effectively now, it has done something. We just don't see anything. It's stored some information in this variable cursive d. What kind of information? Well, if I do this, actually I can make it cursive d by doing escape, scd, escape. Fun. Mean, 3/2. It did an integral, evidently. Variance. We haven't done this. 3/20. Is that right? Let's check it. How about what's the second moment? The second moment's 12/5. Take the second moment minus the square of the first moment. Computational formula for the variance, get 3/20. Standard deviation should be square root of 3/20. Written like that. That is the same as square root of 3/20. About 0.387. Standard deviation of about 0.387, mean of 1.5. Okay, how do we do some simulation? Random variate. But now, unlike what we did before, when we put like normal distribution or gamma distribution in here, I think we just put D. If I enter this as is, it's going to give me one observed value from the distribution, some number between 0 and 2, more likely close to 2 than to 0. There we go, 1.856. Do it again, get a different number. Put a comma 100 here, I'll get 100 observed values. Yep. Most of them are close to 2 rather than close to 0. Store this in something you might call data, semicolon suppressed output, make a graph like a histogram. Looks like our distribution, similar, not exactly the same. It's a simulation. If I do it all again, put this on the same line, I get a different distribution because it's a different simulation. The histograms here are different than the histograms that are described in chapter 6, because with each bar here, for example, this bar, the vertical axis is representing a count, not a percentage. In the reading in chapter 6, you read about histograms where you count what are called relative frequencies, percentages effectively, and those become the heights of the bars. But we're getting a count. So like and you can see there's a 12 that shows up there. There's 12 numbers in this particular data set that are between, looks like about 1.2 and 1.4. The height of this bar is 12, and you hover over it, you see the number 12, it's very small there. Height of this one's 20. Height of this one's 29. Out of 100 data points, 29% are between about 1.6 and 1.8. 29 of 100. The probability of being between 1.6 and 1.8 should be close to 0.29, probably smaller because of this being a high bar compared to what it should be. The bigger the data set, the more accurate the representation of the PDF. See, it's matching the graph of that quadratic now pretty closely, it seems. Data set of size, sample of size 10,000 here. What's the mean of the data? This is an observed value of a sample mean. Very close to 1.5. How about that? I do it over and over again. I always get something very close to 1.5, sometimes smaller, sometimes bigger. But if you average these numbers over many different simulations, the average of these numbers is going to be really, really close to 1.5. And that's true even if I did a smaller data set, size 100, say. The individual means are further from 1.5, but sometimes they're smaller and sometimes they're bigger. And if you do many, many simulations and get many, many observed values of X bar, the average of those numbers should be very close to 1.5. The mean of the mean is the mean. This is an experimental verification of our abstract fact right here. X bar is not the only statistic. There's lots of statistics, though X bar is the most common one. We could also talk about the median. Oh, yeah, that came up on the exam. The median, well, let's do something a little different than the book and actually on the exam. The median is of the distribution. I'll use a lowercase m. Median, lowercase m. The book uses an X with a tilde above it, but I'll use an M. Is the number such that the probability that X is less than or equal to M is exactly 0.5. That's a value of the CDF. So you need to find the formula for the CDF, which you did on the exam, and most of you got it right. Capital F of X is going to be the integral from 0 to X of the PDF If I use a t for the variable of the PDF, that's 3/8 t squared. Integrate that, you get t cubed over 8. Evaluate that from 0 to x, you get x cubed over 8. And so to find the median here, you replace x with m, you get m cubed over 8. Needs to equal 0.5 or 1/2. Multiply both sides by 8 and get m cubed is 4. So m, the median of this distribution, is the cube root of 4. And that ends up being like 1.59, I think. 4 to the 1/3 power. Yeah, about 1.59 is the median of the distribution. It's different than the mean. How do you interpret the median geometrically? It's not the center of mass. It's the x location, cube root of 4 in this case, at which the area under the graph of the PDF to the left of the median is 0.5, and to the right of the median is also 0.5. The mu value, the mean, is smaller because the mean is more affected by outliers. Is a big lesson in statistics. This distribution has a mean that is, yes, closer to 2 than it is to 0. But the tail of the distribution, you'd call this a left skewed distribution, is off to the left here. You've got, once in a while, you get a few low outliers that have a greater effect on the mean than they do on the median, is the intuitive idea here. And you can describe it in terms of data as well. That's a population parameter, like mu is. What's the corresponding sample statistic? We could maybe call it capital M. Does capital M have a formula? Not really. More of a description and algorithm. The observed value of capital M, the sample median, that's a capital M, as opposed to the population median, the little m that we just found, is found from the observed values of the random sample x1 through xn. These are capital X's. Little x1 through little xn. By putting these numbers in order from least to greatest, and finding the middle number if n is odd, and the average of the two middle numbers if n is even. You ever do that kind of thing before? Okay, do I need to write all that? By putting these numbers in order from least to greatest, and defining little m, the observed value of capital M, using the same symbol as the population median. Maybe that's not a good thing. The book calls this x tilde, like that, to be the middle number when n is odd. When n is odd, there will be a middle number. Like if you've got 5 numbers, 1, 2, 3, 4, in order from 1, 2, 3, 4, 5 of them, the middle number will be the third number. If there's 7, the middle number will be the fourth number. If there's 9, the middle number will be the fifth. The middle position is always n plus 1 over 2 if n is odd. And the average of the two middle numbers, arithmetic average of the two middle numbers, if n is even. That's a mouthful, but it's worth writing once. The middle position, so to speak, does have a formula. It's n plus 1 over 2. And that'll be a location of a middle number when n is odd, because it'll be a whole number when n is odd. And it'll be a location between two middle numbers when n is even. Like if n is 10, this is 11 over 2, 5.5. If you got 11 numbers, the middle position is position 5.5, which means the two middle numbers are positions 5 and 6. By the way, what do you do if you got repeat numbers? They're still in the list more than once. So when I say least to greatest, it could include repeats where things are equal. And that does sometimes happen with real data where you've rounded to a certain number of decimal places. So can we do this with Mathematica? Yeah, I think so. Like, can I find the median of the distribution itself? Hopefully we get, what was it? Oh, that was the mean. Well, no, okay, the median. Yeah, you're right. Cube root of 4, okay, about 1.59. Can we find the median of the data set? Yep, close to 1.59. Let's see the data set, though we don't want 100 data points. How about just 7? There they are. Can I put these in order from least to greatest in Mathematica? Yes, there's a way to do it. I'm just forgetting how. Arrange? No. Order? Maybe. Okay, no, not order. I'm forgetting. You can put them in order. I'm just forgetting the command. Let's just see if we can eyeball it here. Here's the smallest number. N is 7 here, so n plus 1 over 2 would be 4. The median is in the 4th spot. That's the smallest number. Here's the first spot, second smallest, third smallest, fourth smallest, I think. And yeah, if you go backwards from largest downward, that'll be the 4th largest as well. So the median of that data set should be what you see there, should be the 1.53807. What other kinds of statistics? How about the sample variance, standard deviation? Sample variance. S squared. Why not S squared? Because S is our version of the Greek letter sigma. Well, okay, sigma is the Greek version of S. Notice it's a capital S. Capital S squared. What should it be? What's a formula for it? Using the random sample. We are motivated by the fact that sigma squared, the variance of the random variable x, is by definition the expected value of x minus mu squared. You remember that? That's the definition. Of course, we know that also equals the expected value of x squared, the second moment, minus the square of the first moment. We are motivated by this definition. Expected value is a theoretical average. So maybe we should take an average of what? An arithmetic average of these kinds of quantities, maybe? Where x gets replaced by like x1, x2, x3 through xn, and you add those numbers up and average them. Sum I goes from 1 to n of something squared divided by maybe n. Hang on, don't write an n. xi, capital Xi, what do we put here? We could try to put the mu. Could try to put mu, but there's a problem with that. Nobody knows mu in most practical applications. So there's a problem with putting a mu there because nobody knows it. So how are you going to compute this? So we compromise and do the next best thing and put an X bar here. But if you put an X bar in there instead of a mu, you have to pay a price. Is it a bad price? No, it's not so bad. Instead of dividing by n, you divide by n minus 1. What? What? What's we divide by n minus 1 instead of n because we lost, in quotes, a degree of freedom. What in the world does that mean? I don't want to explain it. Take it on faith. Replacing mu with X bar caused us to lose a degree of freedom. And because of that, the price we have to pay is we have to do this weird thing of dividing by n minus 1 instead of n. Does everybody divide by n minus 1 instead of n? No, they don't. It's a matter of debate. Should a statistician divide by n or n minus 1? What do most people do? Most people divide by n minus 1, not n. Why? Why? Because it can be shown that if you divide by n minus 1 instead of n, S squared becomes an unbiased estimator of sigma squared. I.e., S squared is an unbiased estimator of sigma squared. Proving this is very difficult. Not impossible, just very challenging. It actually is, the proof actually is in the book, but it's not in the main part of the reading. It's in the appendix at the back. You can look at it there. Takes up on a whole page. Kind of nasty calculations, and you're like, I don't think I want to read that. Or I hope you do desire to read it and try to understand it. But you may just give up, look at it and give up. And it's not bad if you do give up. It doesn't provide a ton of insight. It just offers a lot of practice with tricky calculations to verify this. What does it mean intuitively, though? Whereas with the mean, expected value of X bar equaling mu, it meant the mean of the mean is the mean. This means the mean of the variance is the variance. Doesn't quite roll off the tongue as nicely, but still true. Expected value is a mean. That's a sample variance. That's a population variance. The mean of the variance is the variance. What does that mean? It means S squared. Oh, S squared is a statistic. It's a random variable. It's a function of a random sample. This is like an h of x1 through xn. Kind of a complicated function, and also involves a statistic within it. X bar's got a formula as well. X1 plus x2 plus ... plus xn over n is hidden within this formula. So it's really, at its core, a very complicated formula. It's got a distribution. It's a random variable. It's got an expected value. The expected value of this, if you wanted to compute it by the definition of the PDF of this, whatever it is, you'd have to do a crazy integral, n-dimensional integral, is equal to that. But you can prove this without doing the integral by properties of expected values and some, again, fancy calculations, tricky calculations. Let's think about it intuitively, though. If we go back to our simulation, do our data, say a large data set, well, we can compute the variance of the distribution, use the cursive D. That was the 3/20ths, which is what, 0.15. So hopefully, if I do a variance here, is Mathematica programmed to compute this thing dividing by n minus 1, or what other people do in dividing by n. I think Mathematica does divide by n minus 1, but I'd have to look that up. Anyway, it got something close to 0.15. And if you redo it over and over, sometimes it's below 0.15, and sometimes it's above. There's experimental verification, you might call it. Seems to be below 0.15 more often than above, but okay. That was just randomness. Now it's more often above. Experimental verification, not a proof. Experimental illustration of this fact. Calculators will give you two observed values, one for the square root of this and one for the square root when you divide by n, called the sample standard deviation, or population standard deviation. Yeah, S, the sample standard deviation, is another statistic it is the square root of the sample variance. In a formula, it's the square root of this crazy thing here. Unfortunately, even though S squared is an unbiased estimator for sigma squared, S itself is not an unbiased estimator for sigma. Unfortunately, the expected value of S is not equal to sigma, even though the expected value of S squared does equal sigma squared. What? Really? Can we come up with an unbiased estimator for sigma? Yeah, we can effectively multiply S by a certain constant to make the resulting thing unbiased, but hardly anybody ever bothers. We just appreciate the fact that S squared is unbiased in estimating sigma squared, but S is not, unfortunately. We just live with it. I'm telling you is serious. That's the way people think. Yeah, I'm glad of that. It's a nice theoretical result. Unhappy about that, but there's nothing I can do about it. So maybe we should divide by n instead? No, that doesn't work either. For the standard deviation, it's still not unbiased. Just an unfortunate fact. So what I've been talking about here does combine things from chapter 6 and chapter 7, the beginning of chapter 7. Let's end class by doing a little bit more at the beginning of chapter 7. There is plenty of stuff I've skipped in chapter 6 about certain kinds of graphs. You should know how to make histograms. You should also know how to make box plots, or also called box and whisker plots, though the book's description of them is, in my mind, unnecessarily complicated. I prefer simpler box and whisker plots that just focus on computing what are called the min, first quartile, median, third quartile, and maximum. Haven't had time for that, so I better not give you a homework problem about that, but you should read about it. We'll talk about it a bit on Tuesday next week. But let's end by going in a little bit more depth on chapter 7. In fact, let's end by, for example, proving that X bar is unbiased. Why is X bar an unbiased estimator? Unbiased estimator for mu. We don't have to do an n-dimensional integral to prove this. Instead, we trust properties of the expected value operator to prove it. Properties we already know, in fact. Though to prove those properties does require thinking about higher dimensional kinds of functions and integrals. We've just been trusting these properties. What's X bar? It's that. But that is also the same as 1 over n times x1 plus 1 over n times x2 plus ... plus 1 over n times xn. I could write all this with summation symbols as well. And you should, if you're comfortable with that, you should. From this point on, if you've always felt uncomfortable about summation notation with capital sigma, you should work at getting better at it, because I will sometimes use it. Expected value is linear. The expected value of a sum is the sum of the expected values. Oops, jumped ahead of myself there. And you can pull out constants. The 1 over n's can come out in front. And if we want, we could write this all as one fraction, though we don't need to. What do you do now? Use your assumptions. What assumption? The assumption that x1 through xn is a random sample from a distribution. The distribution of what? The distribution of x. What's x? Our unknown random variable with an unknown distribution. But assuming it's got a mean mu, all these things are the same. They're all mu's. No subscripts. So I've got 1 over n times mu plus 1 over n times mu plus ... plus 1 over n times mu. How many terms? There's n terms here. This is n times 1 over n times mu. The n's cancel. You're left with mu. Done. That, if you believe properties of expected value, proves the mean of the mean is the mean. Assuming the mean of the population distribution exists. There are some examples, I've mentioned this before, where the mean doesn't exist. That's why X bar is unbiased. You can say other things about X bar. This is something you should know for the homework. It's in the reading. You can compute its variance. What does it equal? Not sigma squared, but instead sigma squared divided by the sample size, n. And that's a very good thing. It's a good thing that you divide by n here, because what this tells you is that larger sample sizes result in sample means with smaller variances and smaller standard deviations, meaning they're better estimates when you get observed values of the population mean, mu, because the variance and standard deviation of X bar is smaller when n is larger. So this is a very good thing. So I'm going to give you a few problems from chapter 7 as well. One thing I forgot in chapter 6 that you will need on homework is there's a computational formula for the sample variance that I forgot to mention. This formula right here, you should be able to use. I did not write it down today for data. So replace the capital Xi's with lowercase xi's data. Compute the sample variance with this formula involving these summations. And your calculators do compute these summations, by the way. When you compute your one variable statistics, you'll see the summations. Okay? And then take its square root to get the sample standard deviation. It's page 205, chapter 6.